Alright, welcome. In this video we're going to take a look at the longest common subsequence problem. This problem is commonly solved using a dynamic programming algorithm, and we're going to use it as a tool to study a little bit more some two-dimensional dynamic programming. Before we get into the problem, let's take a look at a couple definitions that will be helpful. First of all, let's remind ourselves that a sequence is an ordered set. We took a look at a sequence earlier when we were looking at the longest increasing subsequence problem. So there we also introduced the idea of a subsequence. So a subsequence we can say is created from a sequence if we delete out some of the elements. So remember, sequence is an ordered set, so order matters, and we create the subsequence by deleting out some of the elements, meaning that the order of the original sequence are maintained among the elements that remain after we delete some. So that's how we create a subsequence. The one thing that we sometimes overlook is that a subsequence does not have to be consecutive in the original sequence. They have to appear in the same order as they appeared in the original sequence, but they do not have to all be consecutive. If we add that requirement that they all be consecutive, that creates the substring definition. So we can think of the substring definition as being an additional criteria on being a subsequence, which is, in addition, a substring must consist of completely consecutive characters in the original sequence. We're going to take a look at a couple examples for the next couple algorithms we'll be looking at. And in them, we're always going to be comparing some strings or sequences, and the strings and sequences I'm going to be considering here will be strings of characters or words. And so the first word I have here is just the word bandana, and we can see here that the word banana is actually a subsequence of bandana, and we can get that by just deleting out the D character. And the word band is a substring of bandana. It is a subsequence, and it is also a substring because it appears consecutively in the original sequence. Now we see banana is a subsequence but not a substring, so we have a couple examples of how we apply those definitions here. Now the problem that we have at hand today has to do with two different sequences. So in this case, my example, I may be given two sequences, bandana and Montana. And the question at hand is, well, can we find the longest common subsequence? So if we have two sequences, they might have common subsequences or substrings. And in this case, we might want to know what is the longest common subsequence. So again, applying the definitions appropriately, we can see that for subsequence and substrings, we're going to arrive at different answers here. First of all, the longest common subsequence is actually the sequence nana, N-A-N-A. Both of them have N-A-N-A appearing in them, and there are no longer subsequences that they have in common. That's maybe not immediately clear. But luckily our brain computers are pretty powerful, and we might be able to see we can't really get any better than that. But again, our brain computers are pretty good, but imagine if the sequences were, say, 100 long or 1,000 long. Our brain computers would be let down by that. We'd want an actual algorithm to help us. So the longest common subsequence is nana of length 4. What about the longest common substring? Well, that's just Anna, then, the A-N-A at the end of each sequence. So there's an interesting thing there, that longest common substring is also a suffix of both strings, actually. And that's going to be interesting when we take a look at the longest common substring problem a little bit later on. So I think we came up with these two answers, Nana and Anna. And if you did, then great, then you're on the same track. But now we're going to want to see how can we, again, apply dynamic programming to try and come up with a good solution to these problems in general. So I have just stated the problems here more formally. Remember, that's step one in our design strategy. But there's not too much here beyond what we've just said. We get two sequences, possibly of different lengths. Montana and Bandana were the same length, but they didn't have to be. And the output is just going to be the length of that longest common subsequence, and we actually want to know the sequence itself. And the only thing I've changed with substring is really this word, subsequence to substring, which means I'm swapping out one of those definitions from the earlier slide there for the other one. So let's just quickly go through one more time the definition or our design strategy for dynamic programming. We just did the first step, which was state our problem as formally as possible. And we know that, like we've seen in many of our examples so far, we need to continue to build these self-reductions, which is a relationship between the main problem and the sub-problems. We want to find some way to solve the main problem by using solutions to sub-problems. And again, if we've done that, then we've shown that we have optimal substructure. But since this is a dynamic programming example, we're probably going to get to step 4 here, which is we're going to identify that there's overlapping sub-problems. And in the cases of overlapping sub-problems, we're going to want to divert from divide and conquer, or we're going to avoid divide and conquer as it's inefficient, and instead apply dynamic programming. So here we are, which means in dynamic programming, we're going to solve the sub-problems from the bottom up. We're going to start at the easy subproblems, and so we need somewhere to store solutions to the subproblems as we go. Well, this video is in the series on two-dimensional dynamic programming, and so in two-dimensional dynamic programming, we need a two-dimensional data structure, in this case, two-dimensional array. So we'll use that, and as I mentioned, we'll have an algorithm that will solve the subproblems in order from the smallest ones up to the main problem that we're trying to solve. And at the end, we'll apply a little bit of analysis to make sure we know how many resources are being used by our algorithm. All right, so let's consider what subproblems we might want to look at for this particular example. And so again, in our minds, we might want to consider that we have, say, the strings Montana and Bandana, if that helps us. So maybe what we might think is if we could find the longest common subsequence of some shorter sequences or shorter strings, then that might help us. And in particular, we have a couple different ways we might make things shorter. But remember that, you know, by convention, we might just start at the end at n and think about cutting off those characters. So what that means is the subproblems that we're going to be looking at are prefixes of the sequences that we have. So remember, a prefix is going to be a substring, so consecutive, starting at the beginning of the sequence. So I've got just sort of a little example here that we have. If we have a string or a sequence here, S1 up to Sn, then S1 up to Sk is going to be a prefix for any value of k from 1 up to n. Actually, from 0 up to n if we include the empty prefix as well, which of course we might do so. So if we only had one input sequence, considering all possible prefixes might be n or n plus 1 if we include the empty one again. Different possible scenarios here that we might need to consider. That would be a one-dimensional problem. But we actually have two input sequences instead, which means we're going to end up considering all different pairs of prefixes. And so one thing I might do here in a second is consider how many such pairs there might be. But we need to come up with a self-reduction now, so I'm just going to use this simple notation here, LCS, longest common subsequence, of n and m, where n will be the length of my first sequence A, m is the length of my second sequence B, and then we can modify those variables to shorten my sequence if I want to consider shorter sequence, cutting off characters at the end of each sequence. And again, since these are optimization problems, I'm not actually going to be worried about the sequence itself, I'm instead going to be worried about just the length of that longest common subsequence or string, and we're going to use that to calculate at the end, maybe extract the sequence that we find. Okay. Right, so imagine we again have our two strings here. It might be helpful for us to use them. And we said we were going to maybe consider prefixes of these strings, and maybe if we knew some of the longest common subsequences of such prefixes, we could use that maybe to build up the longest common subsequences of longer strings or longer prefixes. Now, one of the questions at hand was how many possible prefixes are there? Again, if we include the empty prefix, we would say that there are n plus 1 prefixes of the first one. There would be m plus 1 prefixes of our second string or second sequence. So the number of prefixes we would have together would be n plus 1 times m plus 1. Well, this, of course, is, we can see, is going to be an order of n times m, just the number of different prefixes. So we're going to go ahead and do that and try and compute the longest common subsequences of these by, again, being a little bit clever and trying to combine what we know of shorter sequences together for longer sequences. Now, to do this, we're going to get set up here, and I want to get set up using starting again at the terminating condition when our values are small. And again, when our values are small, our n and our m are small, we have a couple choices here. As always, we could try our n equals 1, our m equals 1. Well, that would mean considering these two values, and it actually kind of depends a little bit on what those values are. Here, because m is not equal to b, that makes it a little bit easy. But if they're equal to each other, maybe if there's an a and an a, that might be a little bit harder. So actually, n equal 1 and m equals 1 is not really the best choice. Let's try n equals 0 and m equals 0. So I'm actually going to set that up here. If n equals 0 and m equals 0, then in this case, what's the length? Remember, we're concerned with the length of the longest common subsequence. Well, if both of our strings are of length 0, then it should be 0. But it's actually more than just in this case. If either of our strings is of length 0, then our output should be 0. So I'm going to just change this here. I'm going to change that to or. Okay, if n equals 0 or m equals 0. And the interesting case there is if we're thinking and we're looking ahead and we're thinking about this two-dimensional data structure that we have, maybe n going this way, m going this way, then our 0, 0 would just be this place. So when we had n equals 0 and m equals 0, that's just this location. But if we have n equals 0 or m equals 0, we're actually talking about both the first row and the first column. Okay, so we've actually changed it up. So our base case is no longer just one location. Our terminating case might be a whole row or a whole column, or in this case, both. Okay, so our first row, first column filled in with zeros. That's going to make things a little bit easier for us. Now what we want to do, we've sort of tackled this end, and we've tackled this end, the terminating case, by saying, well, what if we just consider the empty prefix, the one that has nothing? That made it easier on us. So let's go to the other end here, and actually, if we go to the other end here, we can see there's a good choice or a good dilemma that we have here. But the first choice, we'll notice that in our two examples, and this is sort of by design, we notice that our last two characters actually match. And in fact, this is something that's going to be important for us to check. We want to make a comparison between our two last characters, and I should be careful here, this should be b sub n. So a sub n, that's this a, and b sub n, m, sorry, that's this a, they're equal to each other. So we're going to consider this case. If they're equal to each other, then what that means is we could use them in our longest common subsequence. And in fact, if we could find a longest common subsequence that only used the characters here from mon, tan, and only the characters from bandan, well, however long that was, no matter how long that was, whatever sequence it was, we could add the a to the end and make it one longer. Okay. Now, however long that sequence is, we have an expression for that. That's the longest common subsequence for n minus 1 and m minus 1, right? N minus 1, we cut off one element here. M minus 1, we cut off one element here. And we end up, we said plus 1 on that. Okay, so this would be if n is greater than 0 and m is greater than 0. Plus our additional condition here, when they match. A sub n is equal to b sub m. Okay, so this is one case, but it looks like we have another case here then. If n is greater than 0 and m is greater than 0, so we're still in that case, and a sub n is not equal to b sub m. That's our other case here. So in this case, let's see if we can set this up. Now I'm going to put an x on here. That's just made it up. Let's call it Montanax. So let's say we were actually dealing with a different problem. It was Montanax in bandana. Now the problem here, and the reason why it's sort of helpful to put the x on here, is what we realize is that we want these a's to match up in the next step. Which means if we cut off the x and the a, if we cut off the an and the bm, we're being a little bit overzealous. We're throwing away too much. And we can see here that what we actually want to do is just cut off the x and not the a. And so let's just be careful here. Let's take some notes. If we cut off the x, that's the n minus 1, but not the a, that's this subproblem. Okay. Now, it turns out that worked out fine, but we would rather, or rather not rather, if we had the opposite case where we put the x on the other side, so imagine we didn't have it here, we now have it down here, then we would have the other case that we might have, LCS n and m minus 1, where we've cut off the b but not off the a. And we don't really know which case it is, but one of those cases might be the good case. Okay, we don't want to cut off both of them, and we don't want to cut off neither of them. If we cut off neither of them, then we haven't done anything. We were saying LCS of nm is LCS of nm, and that doesn't get us anywhere. We need to get rid of a character somewhere, and we want to get rid of one of these n characters, but we don't know which one to get rid of, so we're going to get rid of either the one from A or the one from B. And so what that means is, now again, what are we trying to do here? The L here is longest, so we want to take the max of those two possibilities then. The longest common subsequence of n minus 1 and m, or the longest common subsequence of n and m minus 1. Now there's no plus 1 that comes on the outside of this one, because in this subproblem, we're not adding our pairs, our a's that we paired up here onto the end of anything. We just deleted that x or deleted this x for the purpose of, hopefully in the next case, in the recursive call, whichever one we go to, we pair up those a's and we carry on from there. So what we have here actually is a good self-reduction for our longest common subsequence problem. So we can see we have something very similar over here. I just saved myself a little typing over here. So our terminating case, and then otherwise we have our two recursive cases. Okay. We notice one of our recursive cases again only does only looks at one sub problem, whereas our other recursive case looks at two subproblems. Okay, so one is going to be sort of straightforward. We just look here and copy it down and add one. Otherwise, we're doing this max operation. So we've technically got to step 3, which is going to ask us to now see, do we have some overlapping subproblems? Now, the way we're going to see this is actually very similar to the toy problem we looked at in the last video, the dungeon escape problem, where at least these two subproblems, one looks to the left and one looks up. One looks above and one looks to the left. This looks up and to the left. And we saw in the dungeon escape we started getting overlap up to the left. Well, now we're going to get even more overlap. So because we have the same pattern here, we actually do have our overlapping subproblems. So yes, indeed we do. And so let's again apply our dynamic programming then and try and decide what data structure do we want to use to store the solution to our subproblem. So again, usually to do this, I look here at what I'm using for my self-reduction, and notice we are varying both of these variables, so n is being decreased, m is being decreased. So because of that, this indicates we should use 2 dimensions. We have 2 variables here, 2 dimensions. Okay, so we should use a 2-dimensional data structure. And then what order are we going to solve our subproblems? Well, it looks like we're going to start by filling in the zeros, and then, well, what problems do we need to have solved before we can solve our problem? Well, it looks like the one to the left, the one above, and the one up to the left and above. So as long as we go row by row, or column by column, or this strange diagonal, it looks like we have a lot of freedom here. Okay, we just need to be careful what orders we go. Okay. Okay, so the next step in our solution then is to try and convert our self-reduction here into some code. So I'm just going to do that over here. I'm going to call my code the same thing for save myself some writing. But we're going to go LCS here, and I am going to treat it as code. So instead of just having n and m here, I'm going to have my actual input, which is a 1 to n and b 1 to m. Okay. Now also I've got LCS up here. I'm not writing recursive code, so LCS should not show up anywhere down here. So I shouldn't try and confuse myself in any other by having it shown up any further. We should remind ourselves we're doing dynamic programming, no recursive calls. Okay. So the first thing we do is we grab ourselves a data structure. So maybe I will call it L. We already have an A and a B. I'm going to let L. Now I want it to be the data structure I'm going to store these solutions in, and I also need to be careful here because I start at zeros. So I'm actually going to say 0 to n, 0 to m. It's going to be my data structure. I'm going to say be a 2-dimensional data structure. Okay, so that gets us our data structure. That's our declaration. Now we need to do some initialization. Well, actually, in this particular problem, our initialization we see here is a full row and a full column. So I'm going to go ahead and do that with 2 loops now. So our actual initialization will start with a loop, and I'm going to start with my first loop. I'm going to say I is equal 0 to n. Now here I'm using a convention that I like to do. I'm using I to stand in for my n here. So now that I know I is standing in for n, I must be talking about, my I must be in this place, right? Because that's the index over which n is. And now what are we initializing? Well, we're initializing here where either our n or our m is 0. Well, this is actually, our n is changing, so our m must be 0. And it says in this case, this is just 0. Now, some of us might want to cheat and swap it up and put an L0I in there too. Well, remember our n and our m, we don't know if they're the same. So I'm just going to close this one off. And I'm going to write another for loop instead. Now again, you might say, well, I equals 0 to m. No, I use a convention here. I'm going to use I only when I'm talking about this index, this first index over which I sum up to n, or my index goes up to n. And then I'm going to use j for m. So I for n, j for m. And then I can remember that anytime I'm writing my code, as I have here, instead of an n showing up, I have an I. Just like this, I'm going to have L. It must be a 0 in this case now. J here equals 0. Okay, again, I'll close it off with an end. And again, let's continue. This is actually my init all done. So now we just have our recursive case. And the recursive case is going to require nested loop now. Because we have 2 dimension, we end up with a nested loop. So we're going to get for my outer loop, I'm going to go I equals 1 to n on my outer loop starting where I left off here. I did the 0 throw-in column up above there. For j, same thing, 1 to m. And now, well, we actually have two cases here, so I need to have sort of an if-else. So I'm going to say if now, let's compare, and let's be careful. I want to do like an equals bm, but that's not right. My I is in for my n, my j is in for my m. So it's if ai is equal to bj, then L of ij is equal to what? Well, we've got it here. If they're equal, it should be this, which looks like it's going to be L of I minus 1, j minus 1, plus 1. Okay, if that's not the case, then I'll throw an else on here. Otherwise, we're going to be in this case. So then what are we going to do? Well, then I'm just going to say my Lij will be equal to the max, and I'm just going to grab this one up here now. Remember, these are lookups, not recursive calls. So this must be Li minus 1 j, or I j minus 1. Okay. And now we're actually done. We just need to be careful. Where's our answer? Well, actually, in this particular problem, we wanted to know the longest common subsequence of the whole strings. Well, that must be in that last location. So we'll just return our answer, which is stored in that last location, L sub n m. Okay, so that sort of completes our code. And we can maybe take a quick look here to just do an analysis, jump to sort of step 7 here, and see, okay, what is the dominating part of this code? So we have at the top here some declaration. We have these two loops. The first loop, we can see this one, we can maybe put some comments. This looks like it's about theta n. This one looks like it's about theta m. And then again, maybe looking down below here, well, this is an nm. So this thing might be a theta nm. Yeah, that's the dominant one, or about n squared if they're equal. So yeah, we've got ourselves an n times m runtime for our longest common subsequence. All right, let's finish with a quick example, or finishing off with our example. Here we have again, two sequences, bandana and Montana. I've only got the code here for sort of the recursive bit. So let's just remember our initialization is to give us all zeros in that first column. The purple matrix that I'm going to have here, I'm going to use to remember which subproblem satisfied my my max in the case of the max, or if it was the first case, I'm going to remember the diagonal. Now remember, in the dungeon escape problem that we looked at in our previous video, we were just storing left arrows or up arrows. Well, I'm going to do the same thing here. If it was the subproblem to the left that satisfied it, I'll remember left. If it's a subproblem above, I'll remember above. And if it's a subproblem diagonal, meaning it's this first case here where we had the diagonal, I'll put a diagonal one. Okay, otherwise I'm saying whichever one satisfied this max. So let's go ahead and try and apply the logic here. We're going to see that first of all, our B and our M do not match. So we're not in this first case, we're in the else case. And when we're in the else case, we look at the node to our left, or the location to our left, the one above, and we take the max. Well, max of 0 and 0 is 0, and that's it. We just copy it over. Okay. So I'm also going to have to remember left or up, and in this case, when there's a tie, I've decided to break ties by just remembering to the left. Okay. Now what this is saying is the longest common subsequence between B and M is 0. Well, it makes sense. There's no match there. Okay. And indeed, we can maybe have a little look ahead here M does not match with any of the characters in bandana, so we're always going to have 0 versus 0. The max is 0, copy it over, 0. And again, 0, 0, 0, all the way through. Well, O actually doesn't match with anything in bandana either, so the whole next row is also all zeros. Okay. But N does match with bandana, and so we are going to have some changes here. So let's go a little slower. Well, the first couple we know are zeros. So now we have a match with N matching with N. Now that means we're in the first case now. We're no longer in our else case. We're in the if case or the then case, since they match. And in this case, we just look to our diagonal and add 1. Well, our diagonal happens to be 0. We'll add 1, we get 1. And we remember diagonal. That's going to tell us that we were in this case. Okay, so let's continue then. Now, well, let's just maybe make sure. That's telling us that the longest common subsequence of ban and mon is 1. And indeed that is the case, it's n. So continuing now, if we look at the next location, we get a mismatch again, n mismatch with d. But now we do max of 0 and 1 is 1. And again, don't add 1 in this case, but just copy it over, gives us a 1. Okay, remembering to the left again. And so now we'll see this 1 sort of propagates, and will propagate again. And actually now we get another match. But our match is look to our diagonal and add 1. And this actually gives us an interesting case here, that this is telling us that the longest common subsequence of mon and bandan is 1, and indeed it's the n, but there's actually 2 matches, this one here and this one here. So in this case, when we looked to the diagonal, that's saying we got another match. However, we had already had a match, so it doesn't increase the value to 2. It just matches again. We have a tie. Okay, the last case, a mismatch and an A, so we're just going to take the max. Okay, our next row, we have a T. Our T does not match anything, but because we have some 1s, they will propagate. So again, with a mismatch, 0, 0 is 0, 0, 0 is 0, but 0 and 1 is 1, and 1 and 1 is 1. So we'll get 1s filling out the rest. And that's again saying that the longest common subsequence of mont and bandana is 1. We can match the n somewhere. Okay, now that we get into the Anna part here, we're definitely going to get some more, matches. So next up is the A. It doesn't match with B, so 0, 0 is 0. But now our A matches with our A. And again, in a match, remember in a match, we look to our diagonal and add 1. So we get 0 plus 1 is 1. Okay, A and N are a mismatch, but the max of 1 and 1 is 1, so we get another 1. A and D are mismatched, again, max of 1 and 1 are 1. But now again we get another match. A and A match. So we look to our diagonal and we add 1, we get 2. So now what that's saying is the longest common subsequence of monta and banda is 2. And we can see indeed it's now NA, NA. We added that matching A onto the end of the one that already existed, like we sort of thought when we looked at the subproblems. So we can continue now, okay? We can continue and we can look at the next case is still a mismatch, but now it's 1 or 2, the max is 2, the 2 gets copied. And again, for the same reason as before, our A's are a match, we copy a 2, that's just because we had 2 different ways to make this match. There's 2 ways now. Let's just see, for monta and bandana, that na, that's our longest sequence, can be this na or that na, right? Either one, okay? So let's continue. Our n then, we'll keep going with our n. 0 and 0 is 0. Still mismatch, 0 and 1, 1 wins, okay? Now we get a match. Okay, we get a match here. That's going to tell us n, our match, look to our diagonal at plus 1 is 2. And again, now it looks like an. Okay, mon, tan, and ban have a length 2. Okay, keeping going. N and D, mismatch, so we'll take the max as 2. Mismatch again, we'll take the max as 2. But now a match, and our match here is 3. 2 plus 1 is 3. N and A, mismatch, so we take the max as 3. So let's finish our last row. Mismatch to begin, 0. A match, so we take 0 plus 1 is 1. Mismatch, take the maximum as 2. Mismatch, so we'll take the max as 2. A match, 2 plus 3, or sorry, 2 plus 1 is 3. A, mismatch with N, take the max as 3. Here's the match that matters. A and A match, and we take 3 plus 1 is 4. And that tells us the length of the longest common subsequence, which is indeed 4. We took a look at that at the beginning. Now, the question is, how do we recover that sequence? How do we know what that sequence is? This matrix here is only telling us 4. Well, actually, this matrix is telling us it as well. We start in the bottom location here, and we follow the arrows. And there's a little bit more to it than that, which is as you follow the arrows, whenever you go diagonally, you write that letter down. That's one of the ones you share, because remember, we only went diagonal if we had a match. Okay. So for instance here, we can start diagonal means this A, and we can see that is an A that matches. We copy it down. We got another diagonal, the N, we copy it down. We got another diagonal, A, we copy it down. So those last 3 characters we can see are all matches. This is a mismatch. It tells us go left. And then this one tells us go up, where we hit our final diagonal that we see we're going to get. And then once we run off the edge somewhere, that's when we know we're done. So we got 4, and those 4 diagonals on the way were the ones. Now you'll notice if you start somewhere else, say here, we can go 1, 2, 3, which gives us Anna, which is again the longest common subsequence between Montana and, what did I have there, Banda. Okay, Banda. So there's more than one way you can carve that out. Now that we have this information here, we can find all those longest common subsequences of all the pairs of prefixes that we calculated. Okay, I think I want to leave that at that for this video. This is the longest common subsequence problem. In my next video, I want to take a look at the longest common substring problem, which is closely related to this. Maybe sometimes thought as maybe more important problem to, as a computer scientist, you might think of that as sort of more something you use more often. But it's actually not as quite a good an example of dynamic programming, and so while we do want to take a look at it because it's closely related, I leave it to second because of that. So thanks for watching, and we'll see you in the next video.